Horizontal circular motion. In this video, we're going to draw the free body diagram of an object moving in a circle. We'll summarize horizontal circular motion in terms of Newton's second law, and we're going to review examples of horizontal circular motion. So the first example, let's talk about a ball on a string. I just so happen to have a ball on a string. And what we're going to do with the ball on a string is we're going to move it around like that. Now we know that to have an object turn in a circle, we must provide a force which is directed towards the center of the circle. So as this rotates around, if I keep pulling the string towards the center, that object will travel in a circle. So in this case, what we're going to do is we're going to ignore the fact that gravity is pulling the ball down. If I don't move it, you see gravity pulls it down. But if I move it fast enough, it looks like it's taking creating a horizontal path, a plane. It doesn't look like the string is really drooping downward. So we can get away with ignoring mg in this example. So here's a diagram. Ball on a string. The string has a particular radius, and it's swinging around. Looks like it's going counterclockwise with an upward view. If we draw the forces acting on the object, there's only the one force, the force of the string or the tension pulling on the object. We already agreed to ignore gravity, so the only force acting on the ball is the tension of the string. Now if we analyze this free body diagram in terms of Newton's second law, we know that the net force acting on an object is equal to mass times the acceleration of the object. There's only one force acting on it, and so that'll be the force causing centripetal, the centripetal motion, the circular motion. So Fc is equal to mac, and we're going to replace the F net with the tension. So the tension is going to be equal to mac, or mvt squared divided by r. AC is equal to v squared divided by r. As far as the direction is concerned, I've drawn this object intentionally showing that the force is towards the left of the page. And that often suggests that that is the negative direction. That's what how most people would interpret it. But in this case, I want you to understand that that force is always directed towards the center of the circle, no matter the position of the ball. So the center of the circle is always considered the positive direction. So I'm always pulling inward. Inward means positive direction. So just to kind of recap some of the things that I was talking about, the centripetal force is required to turn an object, to force the object to travel in a circle. F net provides the centripetal force, so all the forces added up together will provide the Fc. And in this case, F net in the x direction is equal to Fc, and there's only one force, so Fc is equal to the tension provided by the string. So another example could be a car turning on a flat surface. So here again, there's a view of a car turning on, making a left turn. So if this was the road surface, the car would be going like this, making that left turn. And to draw the diagram, I have a box that just represents all four tires touching the road surface. The car is turning with a radius I have as r. The center of the circle is positive. So when we draw the free body diagram, there are actually three forces acting on the car. There is the car's weight, or gravity, pulling it downward. There's the normal force provided by the road surface pushing back up, countering the weight. And then we have the force of friction acting towards the center of the circle. It is the force of friction that provides the centripetal force. Without friction, the car could not turn. So the force of friction is providing the centripetal force in this case. So if we analyze the free body diagram in terms of Newton's second law says F net is equal to ma. This is for the y direction. We have two forces in the y direction, Fn and mg. Fn minus mg will equal to m times 0. The object is not moving up or down, so the acceleration is equal to 0. So that means Fn is equal to mg in this case. In the x direction, again, we apply Newton's second law. We have F net is equal to ma in the x direction. F net is what's going to provide our centripetal force, cause the car to move in a circle, and that's equal to mass times the centripetal force. Centripetal force is in the same direction as Fc. Fc is directed towards the center. AC is also directed towards the center. That's a very important point. Now we know that the force of friction is equal to the product of the coefficient of friction and the normal force. We always remember this as the fun equation. F is equal to mu n, or Fn. So what we can do is we can take this and substitute the FF in the previous statement, and we'll end up having mu Fn is equal to mv squared divided by r. Now here we said that Fn is equal to mg. We see that in the free body diagram, that Fn is just equal to the gravity acting on the object. So we can substitute the Fn with mg. So now we have mu mg is equal to mv squared divided by r. And as you can see, we have m on either side of the equation, so we can cancel that. And we'll end up with mu g is equal to v squared divided by r. So we can leave the statement like that, but I'm going to rearrange this in terms of v. So v is equal to the square root of mu rg. And that answers the question, how fast can you travel without skidding out? Okay, so this equation right here will tell us that. We see that it doesn't matter how massive the car is. All cars will behave the same as long as the coefficient of friction between the car tires and the road is the same. If you have two different cars with two different types of tower, then that changes the entire scenario. But if everything's equal, the coefficient of friction is the same, the mass of the vehicle does not matter. What does matter is how big the turn is. So the velocity, the allowed velocity, is going to be dependent upon the coefficient of friction and the radius of the turn.